So before we continue on in section 2.2, I did want to say that we have a tutor in our class, Nicholas. Okay, so Nicholas is going to be helping during class activities, and he also will be able to tutor you in the tutoring center. So you feel free to talk to him then or during class as well. I did get emailed this question, 2.1, Mindscape 14. Yes?
Well, also, like, I pulled this one too, and then it told me I got it wrong, and then when it showed me the right answer, like the numbers that they had were wrong.
They probably showed, if you got a problem wrong, they probably showed you a stock answer that everybody gets to see when they did it. But if you want to email it to me, I'd be happy to look at yours and see. Yeah, I'd be happy to look at your work and see. So in this one, there's different numbers for different students. My numbers are that there's 20 pairs total, 10 black and 10 black pairs and 10 blue pairs. You're trying to find one match, then two matches, and then a black pair. So I'll show you the technique, but with your numbers you're going to have a little different work to do. So try and keep an eye on the technique. So we're keeping track of colors. So in our boxes for the pigeonhole principle, we would put black and blue. And then we think about what could happen as we're drawing socks out in the dark and don't know what color we're getting. Because you could get a match with just two socks, but we're not looking at the least that you need. We're looking at what could happen so that you have to keep drawing sock after sock before you get a match. So you could get a black one, and then you could get a blue one, and then if you had one black and one blue, when you add one more, it's going to either be black or blue, so you'll have your matched pair. So the total here is 3 socks. When you need 2 matching pairs, well, you could get that with 4 socks, but you might not, right? You might keep getting black socks. So maybe you start out with 1 black and 1 blue, and then you get 1 more, so that's going to be a match. Say it's black. But then when you draw a next sock, it doesn't turn out to be a blue sock. It turns out to be a black sock too. Well, then you're up to 4 socks, and you still only have 1 matching pair. So we'll add 1 more, and whether it's blue or black, you'll have a match. Because if you had 5 socks that were all black, they would match. If you had 5 socks where just 4 were black, then you'd have 2 matched pairs. But you could also have 3 black and 2 blue, and you would be all right. So 5 socks. Now I need to be sure of getting a black pair this time, and that could happen with just 2 socks. But maybe I keep pulling out blue pairs. Yes?
So wouldn't it be 12 then? Like there's 10 blue socks and 10 black socks?
So this is 20 pairs. So the actual number of socks I need would be if I got all blue socks first, and then finally got the black pair too. So I think that's what you were thinking, but you were thinking in terms of pairs. So these are the number of socks that you're pulling out of the drawer. So I had, if I pull out all the blue socks, that's 20, the whole 10 pairs, and then I need 2 more after that, and for certain then I will get the black socks. So go through yours.
My total is 16, so it would be 18 then instead?
Yeah, so you'd be taking 8 pairs of blue So that's 16 altogether. And then, after you depleted all the blue, you get 2 more that were black. Now you might get the black ones right away, but to be sure of getting the black socks, you'd need 18 socks. Any other questions? Any other questions from the homework? So I'm glad you were looking ahead. That's the way to do it. Make sure you check out 2.2 homework before Friday's class so we can answer questions that you have there. So we were looking at the Fibonacci sequence. Your author has a life lesson there. Unexpected patterns are a sign of hidden underlying structures. And we're going to be seeing that as we look at the Fibonacci numbers. So we're looking at the Fibonacci sequence. Who remembers, what does the Fibonacci sequence start with? 1. What? And then what comes? 1. Now what? 2. Great. So how do you find the next number? Add the previous 2. Go ahead and write out the first 15 numbers of the Fibonacci sequence. That's a likely question on a quiz that you would be able to write those all out. So go ahead and make sure you can do that. You'll probably want your calculator at some point.
How many?
15. Yes. So go ahead and write out the first 15 numbers of the Fibonacci sequence. So just keep adding. So at some point you'll want a calculator probably. If you use your calculator on your phone in class, that's fine. For a quiz, you'll need to get a simple calculator from someone that you can borrow. So you should have just kept adding 2 numbers to get the next number in the sequence. 2 plus 3 is 5, 3 plus 5 is 8, and so on. Well, we're looking for underlying structures here, so we're going to look at ratios. So you'll still need your calculator for these ratios probably. Not the first couple, but after that. So you take the higher number and divide it by the smaller number. So 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, 13 divided by 8, 21 divided by 13, 34 divided by 21, 55 divided by 34, 89 divided by 55, and we could keep going, but I think that's probably good enough for now, okay? So take out your calculator and figure out what these ratios are. We're examining relationships between the Fibonacci sequence numbers by looking at their ratios. So go ahead at least 3 decimal places, please. So I'll go down the row and ask people, and then we don't have to do all of them, okay? So I'll start in front since last time I started in back. Did you get 5 divided by 3? Okay, 1.666, and then because the 6 is 5 or bigger, we round to 7. So I'm going to do 3 decimal places and round to a 7 there. And I'm just going down the row then, so you know which one's coming up, hopefully. You got 8 divided by 5, what'd you get for that? 1.6, okay. 13 divided by 8? 1.625. 21 divided by 13? 1.615. 34 divided by 21? 1.619. And what did you get for the next one? 1.617. And 89 divided by 55? 1.6 what? 18. Thank you. So we're getting to hover around 1.61, maybe 1.62 when you round to 2 decimal places. This ratio is actually used in different areas. One area that these ratios are used is in investments. So this is an example of looking at the ratios of the Fibonacci sequence, only they look at it the other direction. We took a larger number divided by a smaller number. They would do the other way around, the smaller divided by a larger. When you do that, you get the 0.618. So they use those, and then 1 minus the 0.618 would be 0.38. And they use the 50, which is the 2 divided by the 1. And they use that to make an investment system called the Elliott wave theory. We'll see some other areas where the Fibonacci sequence shows up in geometry as we go on through chapter 3. And I think we might see it in chapter 2 yet. At any rate, let's look at this ratio more carefully. We're going to write these ratios only using ones. Does anybody have any questions before we do that? So we have the 1 over 1. Well, that is just 1 over 1. Okay. Then we have 2 over 1. So I can take my 2 and think of it as 1 plus 1 over 1. And I'm going to get a pattern that I can keep going with this. So I'm going to split this into 2 fractions. 1 over 1 plus 1 over 1. Which is still 2, isn't it? But I'm going to write it in this fashion because it's going to fit with the rest of the ratios that have fractions in them. So now I'm going to look at the 3 over 2. So the 3, I'm going to write as 2 plus 1 because of the 2 in the denominator. So because of the 2 in the denominator, I'm going to write 3 as 2 plus 1. And this allows me to split this up into 2 fractions like I did up above. So whenever you have just a single term in the denominator, you can split your fraction up. You just put the 2 over 2 plus the 1 over 2. And then you see the point of writing the 3 as 2 plus 1 was to get this 2 over 2, because now the 2 over 2 is 1. This 2 over 1, this 2 I'm going to think of as a 2 over 1 because I already figured out what that is when it's written with 1s. So where's my marker here? This was the 2 over 1. Follow your equal signs. So I'm going to take and replace that right there with the 2 over 1. So I'm writing what I have using the line above. The line above I figured out 2 over 1 is 1 plus 1 over 1. So I'm replacing that 2 over 1 with a 1 plus 1 over 1. That brings me to the next ratio, 5 over 3. Anybody seen the pattern enough to know how I split the 5 up? Yeah. 3 plus 2. Okay, so I have the 3 in the denominator, so I write the top as 3 plus 2.
What's the point of breaking them down so much?
So we're going to write them only using 1s, and that's going to give us another pattern that we'll see in our Fibonacci sequence.
Using all of the top line of the 2 over 1, like, links to the 3 over 2, like at the end, like the circle or arrow. What is that?
Oh. So this 2 over 1, we found out could be written as 1 plus 1 over 1.
Yeah.
So when I saw the 2 over 1 here, I traded it out for the 1 plus 1 over 1.
I thought it was 1 plus 1 over 2.
The 2?
Yeah, but isn't that a 1 above it?
Yeah, so there's still a 1 above it. So I put there. So I took the 2, that was a 2 over 1, and I replaced it with the line above, 1 plus 1 over 1. So,
But what did you write above the 2?
it's 2.
Yeah.
So this 1 is still there. So that 1 is that one. And then this 2 is from the line above. So this 1 stayed, this 1 stayed, and this 2 became from the line above. Let's try another one, see if that helps, okay? Okay, so I split the 5 up into 3 plus 2, and that lets me split the fraction up there. So the 3 plus 2 lets me write 3 over 3 plus 2 over 3. Okay, is everybody okay with the 3 over 3 being a 1? Okay. This is actually a little bit of a trick right here because these don't match. The 2/3 and the 3/2 don't match. So I'm going to take the 2/3 and rewrite it as 1 divided by 3 over 2. That's a little bit of algebra. Take your calculator and check. Take the 2 divided by 3 in your calculator and take the 1 divided by 3 divided by 2. And you see they are the same thing. And that's because in algebra we say when you have one number divided by a fraction, you can flip this over and multiply it times the 1, and that will give you back the 2/3. So when you have a little fraction, if you want it flipped, you can just put it under a 1 and then it's equivalent. Okay. And here's where we're doing the substituting like we did with the green lines over there. So I'm going to substitute the 3/2 because I found out that all of this right here is 3/2. This is called a continued fraction, by the way, when you go on and on like this with these fractions and fractions.
Hey, where did you get the 1/3? Especially like 3/3 plus 2/3 equals 1 plus 1/3. Where did you get the 1/3?
So this is a 1 divided by 3/2.
Okay.
So you take the 2/3 and you flip it. Like that. And you put it under a 1. And I was showing you in your calculator that those come out the same. So plain old 2/3 is 0.6 repeating, and 1 divided by 3/2 is 0.6 repeating.
So you always put it under 1 and you always flip it?
Yeah, if you want, yeah, you put it under 1 and you flip it. Oh, I see, that's what I did up here too, and I didn't talk about it, did I?
No.
Yeah, sorry, thank you. So there's a 1/2. Yeah, so we had a 1/2, and that's the same as 1 divided by 2 over 1. Okay, so are we okay up to that point? Okay. Well, here's where we're going to say we know what 3/2 is as a continued fraction of 1s. The 3/2 is this whole thing I circled in red. So I can put this 1 and this 1 down, 1 plus a 1, and then under the fraction where I had the 3/2, I put everything I circled in red because that was 3/2. So you're getting 3 fraction bars when you do that. In the line above you had 2 fraction bars. Now you have 3 fraction bars. Because we figured out how to write 3/2 just with 1s over here. So we had the 1 and the 1, and then we replaced the 3/2 with what we had written over here. Anybody have any questions on that one? Well, we can keep going like this. If I do 8 divided by 5, we can split it all up and show all of this. But what's going to happen is you're going to get one more layer over here. So here I had 1, 2, 3 fraction bars. Now I'd have 4. 1, 2, 3, 4. 1, 2, 3. So you can go through all the steps, but you could just go right to getting that extra 4th fraction bar, because we'd be able to, and your book does this if you want to see it in more detail. You can see the 8/5 split up into 2 fractions where you have the 5/3 showing up in the bottom, and then you replace that 5/3 with this. So this right here is the 5/3. So this is called a continued fraction. I had the whole semester in graduate school on that, on continued fractions. What do you think the 101, the 101st Fibonacci number over the 100th Fibonacci number looks like?
Like crazy stuff.
Yeah, that's right. Good, a staircase. Yeah.
Oh my god.
Yeah, so we'll go ahead and write part of it, okay? We'll just put a little dot, dot, dot here, and then we'll go to the end. So it looks like the other continued fractions we wrote. It just has more fraction bars. So this one had 3 fraction bars. The 5/3 had 3 fraction bars. The 8/5 had 4 fraction bars. The 100th Fibonacci, 101st over the 100th would have 99 fraction bars. We did not write out 100 Fibonacci numbers. If I did write out 101 Fibonacci numbers, would I come to the end, or is there more Fibonacci numbers after that?
No, that's it. Stops there.
Who thinks it stops there, and who thinks there's more? How would I find the 102nd Fibonacci number? Add the 101st to the 100th. Okay, so it actually keeps going because there's no end to how big numbers are, so you can keep going and keep adding. That means that our ratio approaches a value that we call phi. Phi is a Greek letter. It's pronounced fee like you owe somebody some money, you owe them a fee. Okay? But phi is the ratio of Fibonacci numbers going on forever, written as a continued fraction. So I'm going to put dot, 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 and I'm not going to end because this just keeps going on forever, just like the Fibonacci sequence keeps going on forever. Well, these other ratios, we had decimal percentages. We had decimal values for these other ratios: 8/5, 5/3, 3/2, 2/1. We found a decimal approximation of about 1.6. We can find a decimal approximation for this as well. We can find the value of phi.
So phi represents what again?
Phi represents if you kept taking ratios of the Fibonacci sequence forever. What value would that approach?
But if it's like forever,
Mm-hmm.
wouldn't that be like infinite?
It would. We're going to talk about infinity quite a bit in this class.
So how do we figure out the value of phi if it's like infinite?
Good question. How do we figure out the value of phi? So take a look at this part I circled in green. We have seen this number that I've circled in green. We've written it down already once today.
Oh,
What is it?
100.
It looks a lot like the 101st over the 100th, doesn't it? Let's
Right.
compare that. Let's see. It has a dot, dot, dot on the 101st divided by the 100th, but it stops because there's 99 fraction bars and then it stops. This one has an infinite number of fraction bars. So it's similar, but not the 101st over the 100th because this has an infinite number of fraction bars. Okay, so it's not quite the 101st over the 100th, but it is, you did write it down once today. Does anybody know what it is? At least if you're taking notes, you did. Hopefully you're taking notes.
5/3.
Pardon?
Is it 5/3?
5/8. You know, that's how many I wrote on the 5/8. Oops, sorry, no fuzziness there. However, with the 5/8, that was this one right here, there's no dot, dot, dot. So this dot, dot, dot means it goes on forever. So it's not the 5/8.
I'm so confused on how to.
Where did you write it? What?
We didn't actually write it, so we haven't found the infinity.
We did write it, yes.
1.618.
It's going to be approximately that. But we're going to see how to find that. Anybody see it?
1.666.
We wrote this down when we wrote phi. This is phi itself. See if I cover this up. That's phi itself. Same thing. Because that dot, dot, dot means it just keeps going on. When you take out the top layer, it still just keeps going on. There's as many fraction bars as there were before. We'll look at this kind of weirdness when we see.
So so the value of phi is infinity?
The value of phi is the number that makes this equation true. Phi is the number that makes the equation phi equals 1 plus 1 over phi true. So phi shows up in its own little equation, which is very interesting. Phi is inside itself. To solve this is just as if you were solving with x's. I mean, phi makes it look kind of weird, but it's just like you're solving with x's, but phi is the variable.
So you could substitute anything in for phi.
Yeah, but phi is a particular number. It isn't a named variable that mathematicians use, so it does have its own particular value. But if it throws you off when you're doing work with it, you could call it x.
What is the value?
Let's go ahead and find the value. What is the value? So let's multiply both sides of this equation by phi. And we get phi squared, and then the phi times the 1 is phi. And then the 1 over phi multiplies times phi, and the phi's divide away. This is a quadratic equation. Does anybody remember how you solve a quadratic equation? There's a particular formula. When you had an x squared in your equation, you had a formula to solve. What? Anyone remember?
Is that like really long one?
I think it might be the really long one. It's a quadratic formula.
Like a squared plus b squared. Wait, no. A plus b plus or minus the square root of b squared minus 4ac all together.
Yeah, you had parts of it there. You probably learned it to the tune of Pop Goes the Weasel. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So you can go ahead and do this if you want. We're not going to go through and solve that because that's the only time we have to look at the quadratic formula in class. It's also in your textbook if you'd like. But phi turns out to equal 1 plus the square root of 5 over 2. What is that approximately? Some of you were saying it. If you're doing this on a scientific calculator that doesn't do everything all at once, you'd first look at the square root of 5. And then you would add the 1. And after that, only after you get that figured out, then you would divide by 2. So here's the 1.618 that some of you were saying. So phi is approximately 1.618. Now we did a lot of math, and you might wonder, I really got a little fuzzy on some of this continued fraction stuff. How much of this do I have to know? So let's take a highlighter or something that you identify what you have to know, and let's mark off on here what you have to know, okay? So you have to know that this is what phi looks like, that it's this continued fractions of ones that goes on forever. You have to know that phi makes this equation true. Phi is 1 plus 1 over phi. You have to know that phi is 1 plus the square root of 5 divided by 2. And you have to know that phi is about 1.618.
So phi doesn't have like a concrete value.
This is the value of phi exactly.
Like not just in that situation.
And this is an approximate value. So I'm not sure what did I answer your question?
No. So like is it just in that situation that phi equals 1.618 like the 1 plus 1 phi? Or is that?
So these are all 4 different ways to describe phi. So you can describe phi in 4 different ways. I thought it was particularly interesting that phi is the number that's in itself. I like that. Does anybody have any other questions? Okay, every natural number, those are just the counting numbers. Every natural number, so 1, 2, 3, 4, 5, etc. Every natural number is either a Fibonacci number or can be written as a sum of non-consecutive Fibonacci numbers. Every natural number is either a Fibonacci number or can be written as a sum of non-consecutive Fibonacci numbers. So non-consecutive mean they're not next to each other. So you'll need your list of Fibonacci numbers for this. You could write it down again. I'm just going to grab my list from earlier.
So like non-consecutive, you mean instead of like 3 and 5, it'd be like 3 and 8.
Perfect. Non-consecutive would be 3 and 8, not the 3 and 5. Good. So let's look at some examples. Okay, let's write 700 as a sum of non-consecutive Fibonacci numbers. To do this, you need to pick out the biggest Fibonacci number you can every single time. So what would be the biggest Fibonacci number we could pick out? Yeah, 610. Okay, that leaves 90 more, because 700 minus 610 is 90. So what's the biggest number I can pick out now? 89. Yeah. And that leaves 1. Okay, so you see you have non-consecutive Fibonacci numbers. So that's why you pick the biggest number you can, otherwise you'll get stuck picking some consecutive ones. Yes?
Why did you do 89 plus 1 and not just 610 plus 90?
So we're using Fibonacci numbers, so the numbers have to come from this list.
Oh, okay.
Let's try another one. How about 400? Okay, so you probably need your calculator on some of these. What would be your first number?
377.
Yes, 377, the biggest one you can. That leaves 23 left, so what would you write next? 21. And now that leaves 2 left, so what would you write? 2, that's right. Okay, so next, how about you do this one on your own? How about 45? Okay, what did you start with? Good, 34, the biggest one you could. That leaves 11 to go, so what did you pick next? 8, good. And then what? 3. Okay, so this is how you would write every number as a sum of non-consecutive Fibonacci numbers. We're going to use that idea to play a game called Fibonacci Nim. I'm going to tell you right away how to win because I'd like to see each of you be the winning player. You might have a quiz question either about writing every number as a sum of a non-consecutive Fibonacci number, being able to do that, or you might have a quiz question on playing Fibonacci Nim. Fibonacci Nim is also your class activity for today, so once we get going on that, you'll need to take a picture. So to win at Fibonacci Nim, I'm going to give out toothpicks. Nicholas, would you mind putting about half of these down each row?
I have a question about Fibonacci.
Yep, we'll go over it on Friday. Can you give about half of these to each row, please? So I'm going to tell you how to play. So I have a cluster of toothpicks, and you'll get a cluster of toothpicks too. Students at home, if you don't have toothpicks, you might use pennies or something like that. Count how many you have. You're going to be playing against somebody, so count how many you have together. And put them out in groups of 5. So you're going to be putting yours together with the person that you're playing against. So you need to know how many you have along with that person. Here, I'll put the rules out. The rules are in your textbook, and it's probably easier for me to just show you. So I'm grouping mine up in sets of 5. When you're playing with the person that you're playing with, you get sets of 5 too, just because you want to keep track how many there are. Now, as long as you don't have a Fibonacci number of toothpicks, you can always win. Okay, and I'm going to tell you how you always win. Well, first we'll see how you play, then I'll tell you how you always win. Okay, so the first person can take as many toothpicks as they want. The second person, or the person after that, always takes between 1 and how many toothpicks are double what the person took. So like, if the person before you takes 4 toothpicks, you can take up to 8. If the person before you takes 5 toothpicks, you can take up to 10. The player who wins is the one who takes the last toothpick. So I'm going to be player 1, and I'm going to take, here's my Fibonacci numbers. I'm going to take 5. So the next person can take between between 1 and 10. Who wants to tell how many I should take? Anybody? Remember, the one who takes the last one wins. 2. Okay, I'll take 2 for the next person. So I can take up to 4, and I'm going to take 3. Okay, so the next player can take up to 6, but remember, I can take up to double what you take. And the one who takes the last stick wins. So tell me how many to take now for player 2. 3? Okay. So I'm going to take, let's see, you said 3? So I can take up to 6, so I'm going to take all 5, and then I win. The player 1 can always win if they do what we just did here, adding up these numbers. But then when you take a toothpick, take this number. So all the time as player 1, I'm always double counting how many toothpicks there are. And in my head, I'm adding it up and taking the smallest number. So when there were 18 toothpicks, 18 was 13 plus 5, so I took the 5. Okay, when there were 11 toothpicks, 11 was 8 and 3, so I took the 3. Okay, so the first player can always win if they're always keeping track of that. Now, if you lose your place, then player 2 can swoop in and get it by doing the same thing. So give it a try. Play against somebody. I'd like you to each be able to win, so give it a try and see if you can. You want to play with that person right there? Okay. And you two are playing through. Raise your hand if you're stuck. So there's 29? Yeah. Okay, so then 31 plus 8. 29, 29 is 21. Now you can take out this.
We're like still stuck.
Do you know how many toothpicks you have? That's a 5, so you know. Do you know how many you have?
1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
If you play together. Who's going to be player 1?
I'll be fine.
How many toothpicks do you have? Total. Altogether.
5 and
You took it. You're supposed to win. But I'm gonna go now.
There's only 4 So now, okay, where'd you put the knife? You stepped in the corner. How would you, who's player 1?
She said the first person was supposed to learn.
There's one on the board.
but I think, oh, right here.
So how would you write 29 and go down to the knife?
Start with 21.
I didn't get it to New York.
Oh, that's it.
And then you pick up the 16. And after he picks, you have to go through this process again.
Oh my God. 16 to 16.
You can take up to 16. You can take as many as you want. It doesn't have to be 16.
Whatever you want.
And then you have to look through the first
So these two are equal.
Take them off to the side.
So these are only.
They're beautiful.
I got what you want. Take that.
I'll go through a sequence with you, okay? I didn't get around to the whole room, but here I'll go through a sequence. Suppose there's 45. There's 45. So player 1 says in his head, or her head, 45 is 34 plus 11, so plus 8 plus 3. So player 1 picks 3. Then player 2, there's 42 left. Player 2 can pick up to 6. So player 2, how many should player 2 pick? I'll just pick anything. Say they take 6. Or let's do 5, that'd be more interesting. So player 2 took 5, so there's 37 left. And player 1 says 37, that's 34 plus 3. So player...
Oh, we can't see.
Oh, thank you. Player... if 37 are left, player 1 says, okay, that's 34 plus 3, I'll take 3 again. And so player 2 can pick up to 6 again. And we just keep going like that. Player 1 can win if player 1 constantly makes Fibonacci sums and always picks the least number in that. Player 2 can snatch the win away, though, if player 1 messes up. Okay? And also, if you start with the Fibonacci number, then player 1 cannot necessarily win either. Okay, so you can try some of this out. The directions are in your book again, and so is the winning strategy. I'll see you in class on Friday. Oh, don't forget to take a picture of this. This is your class activity. And then put the toothpicks at the end of the table. We'll put the containers to put them in.
Yes. Let's just collect back down.